Lesson 13 is devoted to scanning tunneling microscopy, and you might well ask why, in a course on atomic force microscopy, do we spend time talking about another technique? 4 reasons. STM is historically important. The first publication on it came out in 1981, and there was so much excitement about it that it took only 5 years for it to be awarded the Nobel Prize in Physics. And of course that idea spawned the whole profusion of scanning probe microscopes. It's technically important. It is mostly used in ultra-high vacuum to study the growth and surfaces of semiconductors, in particular silicon, which is the basis of our information technology via computer chips. It's a quantum mechanical phenomenon. Physicists really like it because it is a practical application of quantum mechanics, which, when you study it, seems so theoretical as to have nothing to do with everyday life. But it is central to the operation of an STM. And it's the highest resolution of the probe microscopes, and that, in fact, is what I want to spend most of the time in this lesson talking about. First of all, what is a scanning tunneling microscope? It is a scanning probe microscope, which means that there's a sharp tip in close proximity to a sample, and there's some kind of interaction between the tip and the sample that we can measure. In the case of the tunneling microscope, it is something called the tunneling current, and that is a difficult thing to understand on a conventional level. I'm going to give you an analogy for what happens in a scanning tunneling microscope. Here's a sketch of you standing in a room with a wall, of course, and you've got a hold of a piece of string, and you've tied that piece of string to the wall right here, and you're waving that piece of string up and down, and it forms what's called a standing wave, such that if you had a friend taking a picture, there might be a picture like that, and at a slightly different time the string might be in this configuration. Okay. And if we were to come in and inspect this area, right where the string is hitting the wall, what we would see is, in the moment corresponding to the white string there, that would look like this, and the moment corresponding to the gray string there, it would look like this. The point being that both strings end exactly at the wall, and that seems obvious to us. Well, in quantum mechanics, when we're talking about the world of very, very small particles, what that tells us is that there's a possibility that the string might not end exactly at the wall, but kind of extend into the wall a little bit. So just denote that by dotted lines here. Okay? And if the wall is thick enough, then certainly the possibility that there'd be string on the other side of the wall, that would be 0. But if the wall is thin enough, then there's a possibility of some influence of the string on the other side of the wall. An STM is like the following situation. You're on one side of the wall, your friend is on the other side of the wall. You're trying to signal each other by waving the strings up and down, creating standing waves. If that wall is thin enough, there might be some influence across that wall. So you are like the tip, your friend is like the sample, and this influence is the tunneling current that we can measure. You might have heard of something called wave-particle duality. What that means is that very small objects like electrons in a current, depending on the experiment, sometimes they behave like waves and sometimes they behave like particles. In this situation, the electrons are behaving like waves, just like the waves in a string. What is the current? In our everyday classical thinking, if tip and sample are out of contact, we would say the current is zero. If tip and sample are in contact, the current is equal to the applied voltage divided by the resistance of the system. That's just another form of Ohm's law there. But now, because of quantum mechanics, in addition to this on and off thinking, we have another situation that's dependent on the separation between the tip and sample when those separations are small. So when the separations are on the order of an angstrom out to a nanometer or so, then the expression for the current varies between I0, which would be V over R, if you will, times the exponent of minus twice a constant times the separation. I'd like to take a closer look at this equation because it is key to the resolution of STM. If we were to plot this equation representing the current in a scanning tunneling microscope, and we were to plot it on a linear scale where we have current as a function of separation, it would look something like this. It would decay very rapidly because of that exponent. It turns out there's a better way of representing that. If we take the logarithm of both sides, the natural log, after dividing the equation by I0, the base current, what we get is minus twice kappa S. This kappa is important. It's a constant that accounts for all of the other parameters affecting the current that are not the separation. So it has to do with the mass of the electron, the metals that you have chosen for your tip and sample for semiconductors, and the condition of their surfaces. It has a value, a typical value might be 12 inverse nanometers, and that's of course a rather strange sounding unit, but when you're talking about the arguments of exponents, the overall dimensionality of the argument has to be neutral, and because we would measure S in nanometers, then kappa has to be in inverse nanometers. But at any rate, what we want to do is plot the natural log of the ratio of the current to the base current as a function of position separation S. And as you see on the right-hand side of that equation on the right, that is a straight line with a negative slope, and the negative slope is minus 2 kappa. So if you consider a change in separation of 1/10 of a nanometer, 1 angstrom, and use your knowledge of the slope, what kind of change in the ratio of the currents do you get? Well, it's 1/10 of a nanometer times twice 12 So that is 2.4, minus 2.4. And if we think about how much current is going to change, what we do is we take that ratio of currents and we raise E to the minus 2.4. That is approximately equal to 1/10. So by increasing the separation between tip and sample by 1 angstrom, we have decreased the current by a factor of 10. So that is the key to STM's resolution. I have heard of noise levels in STMs as small as 4 picometers, and seeing as that the diameter of hydrogen atom is 100 picometers, that is really impressive. Thus, the vertical resolution of a scanning tunneling microscope is the result of the exponential dependence of current on separation because of the quantum mechanical nature of electrons. But in the beautiful pictures we see of atoms on surfaces, the lateral resolution must be very good as well. Where does that come from? Let's imagine 3 atoms at the very end of an STM tip. The atom closest to the surface is 2 angstroms away. The next 2 atoms back are 2 further angstroms away. We just learned that current falls by a factor of 10 for about every angstrom of separation. That means that the atoms further back will be interacting rather weakly with the surface, whereas the atom on the very end of the tip will be acting strongly. And the difference in current will be a factor of 100, because for each angstrom we get a factor of 10. Thus, it's as if the atom at the very end of the tip is channeling all the current through it. And because it's only 2 angstroms away from the surface, that current doesn't have much time to spread out. This accounts for the very good lateral resolution of STM, on the order of 2 angstroms, which is the size of an atom. In conclusion, I hope you now appreciate the historical and technical importance of STM and how it's based on a quantum mechanical phenomenon that I did my best to explain in a conceptual way, and how that phenomenon leads to the highest resolution of the scanning probe microscopes. I hope you have some time to go online and find some examples of STM images. I think they're really cool.